All right, so we're going to walk through the kind of scratch work portion of proving that for each natural number n bigger than or equal to 1, the sum one of the numbers 1 through n is equal to n times n plus 1 over 2. All right, so we are going to prove this by induction, and the reason that we're doing that is because we're trying to show that this is true for all of the natural numbers that are greater than or equal to 1. Okay, so first we want to start by defining our statement P of n. So P of n is the statement that the sum 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 over 2. Okay, so notice that, for instance, if, again, this is just an example, that if n was equal to 7, then we'd have the sum of the first 7 numbers, and that would equal to 7 times 7 plus 1 over 2. Okay, so again, I'm just kind of throwing that in an example to make that seem a little bit more concrete. All right, so there's our statement, and when we're trying to prove something by induction, we want to do first what's called a base case. So this is going to be our lowest value of n. In this case, it's going to be n equals 1, since we're trying to prove it for numbers that are greater than or equal to 1. All right, so in this case, we're basically checking that the left-hand side and the right-hand side are equal to each other when n is equal to 1. All right, so if n is equal to 1, then the left-hand side is, of course, just 1, right, because we don't have anything else to add to that. And then if we plug in 1 for n into the right-hand side, we get 1 times 2 over 2, which, of course, this is 1 times 2 over 2, and then the 2's cancel, and it's 1. And so since 1 does, in fact, equal 1, we check out our base case that it works. All right, sometimes, again, this isn't our formal proof, but because it's not our formal proof, we might want to check some other cases just to kind of make sure that we actually believe that this statement is true before we try to prove it. So what is this? If we plug in n equals 2, we get 1 plus 2 on the left-hand side, which is, of course, 3. And then on the right-hand side, those 2's cancel out, and 2 plus 1 is equal to 3. 3 is indeed equal to 3. If we wanted to do one more just to kind of convince ourselves a step further / practice with what this formula actually means before we try to prove anything about it, then we plug in 3 for n. So on the left-hand side, we have 1 plus 2 plus 3, which is, of course, 6. And then on the right-hand side, we'd have 3 times 4, which is 12 over 2, which is, in fact, 6. So that checks out as well. Okay. Again, this is kind of our scratch work for the base case. And so our scratch work for the inductive case, so for this is basically we want to prove that if P of k is true, then P of k plus 1 is also true. All right. So remember, this is an implication. When we're trying to prove it, we assume this part. So we assume P of k is true. All right. Well, what does that mean? That means going back up here to our statement and plugging in k for n. Plug in k for n. All right, so what does that look like? That looks like we have the sum of the numbers 1 through k. And then on the right-hand side, it would be equal to, again, replacing that n with a k, it would be k times k plus 1 over 2. All right. Now what we want to show is that the conclusion, which is P of k plus 1, is also true. All right, so what does that mean in this case? That means that when we add the numbers 1 through k plus 1, right, so that's kind of just one number there, then we get the right-hand side with k plus 1 plugged in for n. Whoops. Stop moving. Sorry, guys. K plus 1 And then, okay, so plugging in k plus 1 for n, up here would be k plus 1, and then k plus 1 plus 1 over 2. All right, which of course looks a little bit silly, because normally we would write that as k plus 1 times k plus 2 over 2. All right. So of course not changing what's on the left. Okay, so this is what we want to show. All right, well, we can't start with what we want to show. We need to start with what we know, and what we know is what we get to assume, which is this equation up here. So I'm going to take this and write it down again, just switching to blue for fun. All right, and since we want to show that this equation right here is true, well, it makes sense, since right here we have the sum of the numbers 1 through k, and here we have 1 through k. We can just add this last term, this k plus 1, into our left-hand side over here. So here we want to add k plus 1 to each side. Okay, so we're adding it to each side because, of course, we still want it to be equal. But then this left-hand side is going to look like this up here, which is what we're trying to show. Okay, so I might run out of space here. Okay, and I'll just put parentheses around that k plus 1 to make it kind of a little bit more obvious that we've added it. All right, so take a minute to make sure you agree that this equation that we just wrote down is the same as the one above it, which we know is true, except for the fact that we've added k plus 1 to each side. But that's okay mathematically, that's okay in an equation, because that doesn't change the value of anything. Okay, so what we need to do at this point is try to show that this right-hand side looks like the right-hand side up here. Again, we're trying to see if we can get it to look like what we're trying to show is true. Well, from here, it makes sense. From here, it makes sense to add those two pieces together, which means that we would need a common denominator. So, I guess I'll make that in red. We'd multiply that second part, that k plus 1, by 2 over 2 to get a common denominator of 2. All right, so this would be k times k plus 1 over 2 plus 2k plus 1 over 2. All right, so now they both have a common denominator. We can add them. So we have k times k plus 1 plus 2 times k plus 1 over 2. All right, so since both those fractions have the denominator 2, we just combine them together. All right, and now on kind of the numerator over here, those pieces, this one and this one, both have a factor of k plus 1, so we could pull that out. All right, so it would be k plus 1. The first term, what's left over is a k. The second term, what's left over is a 2. Whoops, sorry. So that gives us k plus 2 down here. In fact, let me rewrite that because it's a little sloppy. K plus 1 times k plus 2 over 2. Oh, but wait a second. Look, here on the left-hand side, we had the sum 1 plus 2 plus 3 plus k plus 1, all right, which was the same as our thing over here, that what we were trying to show. And then we've gotten through all this lovely work here, we've gotten that it equals k plus 1 times k plus 2 over 2, which is exactly what we were trying to show over here. Okay, so by adding the k plus 1 to each side and then simplifying, we're able to show that assuming that p of k is true, which was this part up here, then we showed that p of k plus 1 is also true, and that's our inductive step, okay? So why that's powerful is because if this is true for a natural number k, if the statement is true for a natural number k, and then it's true for k plus 1, then that means it's true for all the natural numbers, because basically, or sorry, all natural numbers bigger than or equal to 1 in this case. Because basically every time we add 1 to our value of n, or our value of k, it keeps being true. And that's what's powerful about induction. Okay, so I'm not going to write up the formal proof kind of in video form, but it is below this video in the notes. So you should read through it and see how